Alrighty, hopefully everyone's still on board as far as our ratios and proportions are concerned. The next question is, what do we, now that we know what ratios and proportions are, how do these directly relate to what we're going to be doing with, how do these directly relate to what we're going to be doing with this next unit? Because you mentioned triangles. You promised us triangles, Mr. Foster, but all I've seen are, measure some internal angles and things like that. How can we know that what you're going to be doing is giving us actual triangles? We've been promised triangles. We want triangles. Don't think that I don't read those mean tweets. I understand all those mean tweets. I understand you want triangles. Here, I'm going to give you triangles. So, what we're talking about here is scale factors and congruencies. Now, in Unit 2, when I talked about things that were congruent, and I basically said that congruent was essentially equal, was basically the same as equal. This isn't entirely the case. For the time that we were in, congruent meant equal, but you got to remember where we were in Unit 2. We started the unit with a vocabulary dump that was super, super thick and super deep and complex, and there were students that were getting secures and double E's that were saying that they were a little bit nervous about this upcoming one because the vocabulary didn't make any sense. And after 2 days of trying to work with the vocabulary, I ended up restructuring the entire lesson to make sure that everyone was basically on the same page and everyone could do the vocabulary with this new unit as well as could be hoped. At the same time that this was all happening, the word congruent came up, and I had people asking me what was congruent as opposed to what was equal. In order to discuss what congruent was, I would have had to throw in more vocabulary, more definitions, more ideas, and more concepts into a unit that was already so burdened down with ideas and concepts and conditions that I basically just told everyone congruent means equal. Just work with it, just work with it, having congruent meaning equal. Just work with it that way, we'll be all right. And thankfully, everyone was on board with that. They were like, okay, I can live with congruent being equal, which is good because that's what it was. The thing is about congruent is it's like equal, but there's an extra dimension to it. It's like being equal, but like I said, there's an extra dimension to it. If something is congruent, then that means that it is proportionally equal. So what does that mean? If two things are exactly equal, that means that if you've got two sides if you've got two sides of a polygon, one of them is measure of length 4, and the other one is measure of length 4. They're both equal. There's no doubt about it. When you measure them, they have the exact same number. That is equal. That is always going to be equal. When you have two angles that measure 30 degrees, those are equal. Those are always going to be equal. There's no getting around the fact that they're equal. One of them is 30, the other one is 30, both of them equal. We're all on the same page. Congruent means proportionally equal. And what that means is that within the context of a ratio, they are proportionally equal. And so whenever you say that angles are congruent, that angles are equal but triangles are congruent, what you're basically saying is if I have one triangle that has the same proportions of another triangle, so it's not the exact measurements, but if I can take every single side of one triangle, apply a scale factor like we had with dilation in the last unit, and get all the same sides as another triangle, so say like we have a triangle that has all three sides measure of 3, and I apply a scale factor of 2 to all three of those sides. If I have a triangle that has all sides measure 6, I can say that those two triangles are congruent because every single side falls into the same ratio, relationship as all the other parts of the triangle. And so even though they're not specifically equal, because you have one side that's angle 3, you have one side that's measure 3, one side that's measure 6, because every part of the triangle conforms to this ratio or scale factor, we can now say that those two triangles are congruent or similar, which is kind of the root of this unit. We had to start out with ratios, we had to start out with proportions, because now when we're looking at triangle similarity, or we're looking at congruency, or we're trying to relate those concepts together, we have to understand that things can be related or similar without being equal. And if we know the scale factor, if we know that two triangles are congruent, or it doesn't even have to be restricted to triangles, if we know that two shapes are congruent, and we know what the scale factor is, then that means that if we know something about that first shape, doesn't matter what shape it is, then we know everything about that second shape. All we would need to know is what the scale factor was. We would be able to tell you what the side length is. We would be able to tell you what the angles are. All we would have to do is know that they were, all we would have to do is figure out if they were congruent. Similarly, we can do the reverse of that. If we have two shapes, like two triangles, or two, like I said, two shapes in general, and we can show that all three of their sides, or all three of their angles, or whatever they have, are all proportionate or all follow the same ratio, we can say that those two triangles, or those two shapes, or those two ideas are congruent. And if they are congruent, then what we know about one, we know about the other. What we know about the second one, we know about the first one. It basically just means that we have a lot more information about both of the shapes that we didn't have before. And once we know that two things are similar, now we can start using those properties in order to solve different problems. So before we got to congruency, we had to understand ratios, we had to understand proportions. And so now that we do understand ratios and proportions in theory, now we're going to take a look at scale factors. And once we get scale factors, then we're going to get to similarity. Once we get to similarity, then we're going to start talking about what we're going to do with the rest of the unit. But the first thing that we have to do first is we have to talk about scale factors and ratios. So what is a scale factor of triangle ABC to triangle DEF? Well, with the scale, so a couple things first of all, looking at these drawings. If you notice here, each of these angles has little lines on them. What these are little measurement lines. And so it doesn't matter what the measurements are. If you see one line here and then one line here, that means that these two are the same angle measurement. Remember, like I said, the congruencies, usually the congruencies and proportions affect the sides of the shape, or affect the size and the physical dimensions of the shape. What will not change between two congruent shapes is the angle measurement, because 30 degrees on a very, very small device, on a very, very small shape, is the exact same angle measurement as 30 degrees on a very, very large shape. And so that's why we can say, that's why when we see this one little loop here, we know that these two angles are going to be equal to one another. The same way we see two loops here, these two are going to be equal. We see three loops here, we see that these three are going to be equal. That's just a notation detail that we need to know, that we're going to pick up now. Kind of keep in the back of your mind, because it's going to be one of those solutions for similarity. But let's see, what is the scale factor of triangle ABC to triangle DEF? So obviously ABC is smaller than DEF. So whatever the scale factor is, it's going to be larger than 1. So let's see, I've got 8 to 12, so that increases by 4, 10 to 15, so that increases by 5, and then 14 to 21, so that increases by 7. Well, that's not great. That's not great. So what we can do, what we need to be able to do is figure out, so they don't increase by the same amount. But the thing is, they're not going to, because each of the sides are going to be different. They're going to increase by the same proportion. They're not going to increase by the same amount. And so what we need to do is we need to look at what is 8 to 12, and we're told that the scale factor and that they're similar. So we can do this right now. We're told 8 goes to 12, and so what I'm doing is I'm taking a look at the relative sides. And so 8 is the side between angle 1 and angle 2, and so angle 1 and angle 2, that's 12. 10 is the side between angles 2 and 3, so that gives me 10 is to equal 15. And like I said, what I'm doing is I'm just establishing ratios like we did last time. The scale factor is going to tell us what the ratio is. And then finally, I've got 14 to 21 because they're both between angles 1 and 3. So that gives me 14 over 21. Well, here's the thing. I can kind of look at these, and just through years of practice, I can tell 8 to 12, if I divide both of those by 4, that's going to give me 2 to 3. 10 to 15, if I divide those by 5, that's going to give me 2 to 3. 14 to 21, if I divide both of those by 7, that's going to give me 2 to 3. And so the scale factor that you're looking for is going to be whatever that ratio is that gets you from A all the way up, that gets you from triangle 1, here we go, I'll just do this, that gets you from triangle 1 all the way up to triangle 2. So, so what is the scale factor of ABC to DEF? That one is going to be 2/3. And then what is the scale factor from DEF to ABC? Well, that's just going to be 3/2. Whatever this value is, you're going to divide it by 3, which is 5, and you're going to multiply it by 2, which gives you 10. So there we go. So yeah, so the first step if you know that they're going to be congruent, or if you're checking to see if the two triangles are congruent, check to make sure that all of the sides conform to the same basic ratio. Because if they conform to the same ratio, that means that they're all proportional. If they're all proportional, that means that you can shift back and forth between them with a scale factor, and then finally you can solve for, that means you can solve for whatever else. You can do all the magic congruency stuff that I was talking about earlier. So what is the ratio of the perimeter of DEF to ABC? Well, this one's going to take a little bit more math. 12 plus 15 plus 21. So the ratio is going to be, I'm just going to write it out over here just in case it turns into something I don't like. So perimeter of DEF is going to be 48, and then 8 plus 10 plus 14. That's going to equal 32. Just looking at that, I know that I can simplify this farther. They're both divisible by 8, so that's going to give me, divided by 8, that's going to give me, no, that doesn't seem right. Well, I guess it does. 48 divided by 8 is going to be 6, and then 32 divided by 8 is going to give me 4. Ah, that's right, 6 to 4, and then which also reduces if I divide both of them by 2. There we go, Mr. Foster, get it out. Divide both of them by 2. That's going to give me 3 to 2, which is the scale factor also from DEF to ABC. So you can see, by way of a roundabout proof, that I obviously knew what was going to happen. The same ratio will affect the perimeters as well as the individual sides. So we're in good. So yeah, that's pretty good. So similarity statements. The symbol for similarity. Oh, here we go. The symbol for similarity is just going to be this. It's going to be the little wavy line. It's just going to be like the little wavy line. Like the top left of your keyboard is going to be like a little tilde. That bell should be going around any second. But anyway, write a similarity statement for the triangles above. Well, that one is just going to be very basic. It's going to be a triangle ABC. And then you're going to use your symbol for similarity here. And it's going to be triangle ABC is similar to triangle DEF. And so that is the base, and so those are some of the basics of similarity. So let's see. All right, here we go. List all congruent angles and write a proportion that relates to the corresponding sides. So we know immediately that triangle JKL is congruent to PMN. Well, the problem is that they don't look that way. They're kind of, it's sort of, we're told that they're congruent, but there are a couple of things that are not readily apparent about them. But I'll tell you, just based on how the triangles are written, this is what you need to look out for as to what some of the basics are. The general shape looks about the same. So if you take this one and kind of rotate it up, turn it counterclockwise just a little bit, then they would fill out. But the question is, how do I know that it's just this way and not like rotated this way also? You know what I mean? So the way that you tell is by how the triangles are named. Triangle JKL, that's not just an arbitrary, triangle JKL isn't just an arbitrary name, it's not just an arbitrary title. we're saying that triangle JKL is going to be the same as triangle PMN. So what that means is that K is going to be proportionate to M. We also know that since these are the first letters that are going to be listed here, J and P, we know that J and P are also going to be equal to one another, are going to be proportional to one another. And then that means that L and N are going to be the final ones that are proportionate to one another. So the first thing you want to look at, if you are given that two triangles are similar to one another, the first thing you're going to look at is what the name, the first thing you're going to look at is the name. The order that the letters appear in for the triangles is going to be the order of proportionality for their angles. And so, like I said, JKL, so if you have JKL, that means that angle J is going to be proportional to angle P, angle K is going to be proportionate to angle M, and angle L is going to be proportionate to angle N. Well, now that we've got that worked out, now that we have the angles worked out, I know that these are going to be, now that I have these angles worked out, I know which ones are going to be proportional with each other. So angle J is going to be proportional to angle P. Then angle K is going to be proportionate to angle M. And then angle L is going to be proportionate to angle N. All right, now that we've got that worked out, we can also take a look at the sides. The way that you want to look at the sides, the best way to look at the sides and proportions as far as being proportionate with one another, whatever the side is that's opposite the angle, that's the best way to label it in terms of proportionality. And so what I mean is, if I've got the side opposite angle, okay, so for every triangle, you're going to have a side that is opposite the angle, and that's basically going to be the side of the triangle that the angle does not directly touch. And so angle P, I'm just going to use angle P because it's the one I looked at first. Angle P, it touches this side here, and it touches this side here, but it doesn't touch side M, and that doesn't touch the side NM. And so what that means is that side NM is considered opposite of side P. What does this mean? Technically, it doesn't really mean a heck of a lot. But what it does tell us, oh, there's a bunch of stuff. All right. But what it does tell us is that whatever the length of P is, it's going to be whatever the angle P is, it's going to be proportional to angle N and M. The same way that whatever side KL is, it's going to be proportional to J, because these two are both equal. These two angles are equal to one another. So whatever these lengths are, they're going to be proportional to one another because these two triangles are similar. So what does that mean? Side JK is between 2 and 1. That's going to be proportional to, I'll say PM. And kind of going back to what I mentioned with opposite angles, the best way to label them is whatever the angle count is. So I've got 2 lines here for P. That means that this side is going to have 2 lines here. Angle J is going to have 2 lines here, and then 3 lines here, and then 1 line here. So it's 3 and then 1. What these denote are proportionality. Within the individual triangle, if you see 2 sides that have the same hash marks, that denotes equality. But if you have 2 similar triangles, as far as notation is concerned, that means that this side is proportionate to this side. The 2 angles mean that this side, the 2 hashes indicate that this is proportional to this. And what determines how many hashes are on what side? Like I said, and I poorly explained earlier, the number of hashes that are on a side, I determine based on how many circles there are on a particular angle. And so it's completely arbitrary. And so the labeling itself is completely arbitrary. What matters is the relationship that the notations imply, or that the notations infer. So I know that JK is proportionate to PM. Alrighty. I know that KL is proportionate to MN. And then I know that JL is proportionate to PN. It's not PM. N. There we go. So yeah, that is how we will notate congruency with angles, congruency and similarity. With angles, it's little loops, and then with the sides, it's going to be the little hash marks. And like I said earlier, and like I mentioned earlier, say you have a triangle that has all three angles with one loop. That means that all three of these angles are equal to one another because they're all part of the same triangle. But if I have two triangles, and I'm just going to put this one here. But if I have two triangles here, but if I have two triangles with the same angle, what it means is that these two are the same angle and they're proportionate to these two. But these two angles are equal to one another because they're part of the same triangle, but they are also proportionate to these two angles. These two angles are also equal because they're part of the same triangle. So if you see two of the same like little loop here on the same triangle, it means that they're equal. But if you see if you see two little loops here and then two little loops on a different triangle, it means that these are proportional. So same triangle means they're equal. Different triangles means that they're proportional. So yeah, I just realized that this has got this is quite a worksheet. So we shall continue on. Alrighty. We know that triangle XYZ is similar to triangles RYS. All right. So I've got XYZ and then RYS. So what does that mean? That means that it means that angle Y is going to be proportional to angle Y. I don't feel I'm jumping off too great of a height as far as that one's concerned, as far as concepts are concerned. But what it does mean also is that angle X is going to be proportional to angle R, and that angle Z is going to be proportional to angle S. So if we're looking at, so we'll take a look at this. I'll say X, Y, and then Z. That also means that X is going to be proportional to R, and then S is going to be proportional to Z. All right. So what that also means is, oh, this is going to get confusing. I'm just going to stick with the angles. I'm not going to label the sides this time because they're part of the same triangle and the labels would just get in each other's way. So if we know that all of these two triangles are proportionate, we know that the long side here, X and Y, is going to be proportional to the long side R and Y. We know that I'll say the southwest side, X and Z, is going to be proportionate to R and S. And we know that Y and S is going to be proportional to Y and Z. And if you notice over here, it wasn't just an oversight. Oh, there we go. If you notice over here, it wasn't just an oversight. I didn't put I should have put Y and Z up top and put Y and S down here. That way all of one triangle was on one side and all of one triangle was on the other. That's not necessary. That's not a required standard because the thing is, if they're proportional to one another, or if they're equal to one another, or they represent the same proportion, then it doesn't really matter what the listing is. Now, you do have to be a little bit more precise, specifically if you're going to be saying this triangle maps to this triangle. But if we're just talking about general proportions and numbers aren't involved, where you label them and how you label them isn't really as crucial. So next we're going to go on to quadrilaterals. Does the same hold true for quadrilaterals? They absolutely do, especially if we know that JKLM, so J is from J, K, L, M is proportional to Q, R, S, P. So again, you're going to follow with what sides are labeled, and you're going to follow by writing out that those angles are proportional to one another. And so again, we have angle J, proportional to angle Q, angle K, proportional to angle R, angle S, proportional to angle P, angle L, and then angle M proportional to angle P. So we're starting out with our similarity statement, and once we know they're similar and we know their relative shape based on what the points are that they're listed, we know that these are proportional. We know automatically. Now, the catch is that if we start out knowing nothing about them, but we knew that all four of these, but we knew the relationship between all four of these, we could then turn around and say, well, these two quadrilaterals are now similar. And so it's just a question of what do you know to start out with, and using that information about what you know, what else can you find out about it? Right now we're starting with these two shapes are similar, so what can we find out about them now that we know that they're similar? So in this case, side JK is between angles 1 and 2, and so that's proportional to QR. Side, so I'll just write these in, side KL, side LM, and then side MJ. So KL is between angles 2 and 3, so R and S. L and M is between angles 3 and 4, so SP. And then MJ is beside angles 4 and 1, and then that means PQ. So when I talk about being between angles, here's the main thing that I'm looking at. All right, not really. I had to take a quick break away from filming for a second, so I'm not exactly sure where I stopped at. So yeah, when we're dealing with similarity, usually if we're starting with similarity, we can infer all these different relationships. And like I said, the main reason that I'm going along and I'm talking about the side being between angle 1 and angle 2, where this is angle 1 and this is angle 2, it's basically just a way of making sure that we all know what it is I'm talking about, that we all know what angles it is that I'm talking about. Because, like I said, the shapes are rarely put in a position where we can actually compare them directly. So, again, that's why I always use the convention. The first letter of it is going to be proportional. The second letter is going to be proportional. Third letter, etc. And then I just label the angles as we go along. There are variations to this that we'll do, but otherwise we just gotta. We'll run into those and we'll deal with those as we run into them. So next, we have scale factors where we have a scale factor of 2 to 3, find the value of x. So what this means is that we're just going to set up one of those direct proportions like we solved in the previous exercise. If we're going from 2 to 3, what that means is that the small side is 2, the large side is 3. Well, if it's 2 to 3, that means that the small side is going to be 42, and the big side, 3, is going to be x. So 2x equals, I'm not even going to try to do that. Let's see, 42 times 3. So 2x equals 126. So x equals, divided by 2, 63. There we go. And it is really that simple. Once we know that they're similar and we have the scale factor, like I mentioned earlier, then we can solve everything that we need to know about each side, each angle, etc. So say that, again, these figures are similar with a scale factor of 6 to 5. Find the value of x. Okay, so if we're going 6 to 5, that means that we're going from big to little. So 6 to 5 is big to small. X is big, 28 is small. Now that's no big deal. I'm going to go 6 to 5 equals, and then I'm going to say x to 28. And the best part about proportions and cross multiplication and solving things out like this is that it really does not matter what side we put on top, what side we put on bottom, because it's like I could rewrite this as 5 over 6, 28 over x. It doesn't matter. We're still going to get the same answer. All that matters is that we attach the same. All that matters is that if we're referring to the part of the ratio that's 6, that's the one that we put on x, and then if we're looking at the one that references 5, that's the one we're putting on 28. And so as long as those two numbers are paired together correctly in the same relative position, now that means we're in good shape. So we'll do 5x equals 5 times 28 equals 140. 40, that's good enough. X equals 28. 6 times 28. Okay. There we go. Like I said, it's always good to just kind of have one of those little memory things where it's like I have no idea where I think I just typed it in incorrectly. So 6 times 28 is equal to 168. That makes a little bit more sense. Divided by 5 equals 30. X equals 33.6. All right, that makes a little bit more sense. Got to be able to type in the numbers correctly into the calculator. That's the important part. So now we have to find, if we know that we know what the similarity is, we have to find the value of x, but we don't know the scale factor. That's okay. We don't need to know the scale factor. In this case especially, we're given 2 of the sides. We don't need the scale factor. In order to set up the cross multiplication ratio, we need 4 numbers. We have 4 numbers. So all we have to do is figure out what side goes to which. So angle A is angle D, angle B is angle E, and then angle C goes to angle F. So 1, 2, 3, 1, 2, 3. All right. So the side between A and B and D and E, those are the ones that are proportionate. So that means X over, so X is to 25, oops. So that means, so I'm looking at angles 1 and 2, and then angles 1 and 2. So you can see it's not only flipped around this way, it's also rotated, but it's the same shape. If you remember our geometric transformations, it's reflected and then rotated, but it's still going to be the same shape. It's still going to have the same angle measurements. It's still going to have the same side length. But X is to 25, because these are both the 1 to 2 sides, so 1 to 2, 25, as 28 is between the 2 and 3, is to 20. So we have, yeah, x is to 25, as 28 is to 20. So big is to little, as big is to little. So now all we have to do is 20x equals 28 times 25 equals 700. So x equals 700 divided by 20, 35. So there we go. As long as we have 4 sides, we don't need a scale factor. But if we only have 2 sides, then we kind of do need a scale factor. But if we have 4 sides, we can find the scale factor on our own. That's no big deal. So all right, let's take a look. We've got another one, PQRS. So all right, so P, W, Q is to X, R is to Y, and then Z is to S. All right, 1, 2, 3, 4. 1, 2, 3, 4. It's getting a little busy, but like I said, I like doing this so that I have a general idea of what angles lie where, because now when I'm looking at sides, I'm looking at sides between angles 4 and 1, as opposed to angles between this one where I'm rotating it around this way and I'm turning it around this way. Yeah, this way I'm just looking at the side between 4 and 1, because the side between 4 and 1 is the same here as it is here. I just have to have the 2 reference points, and so I'm in good shape there. All right, so I'm solving for, where is it? So I'm solving for x, the side between angles 3 and 4. Okay, so x is to 32. So the x is to 32. And then what are the other sides I have? Side between 1 and 4 as 75. And 75 here, 1 and 4 is 240. So again, when you're setting up the ratios, you're going from big to little. You're setting up the ratios like this. You're basically recreating the scale factor, or what would be the scale factor. So going from big to little is the same as going from big to little. And so that's what we're doing here. And by setting up the two ratios this way, or setting it up so that because these are similar, these are going to be the same ratio. They're going to be the same fraction, which is how we can get away with doing the cross multiplication and having it work. So that gives me 40x equals 25 times 32, 2400. That means x equals 40, 60. So there we go. That is the value of x. And yeah, that's we're doing pretty. I think we're doing pretty well. We're doing pretty solid for a second worksheet. Oh, there's more. Ha ha ha. I know it's you're going to get this on a Wednesday, and I imagine it's going to carry through till Thursday. That's probably okay. But again, we're going to be taking a look at the yeah. Oh, oofa. Alrighty, all right. So again, we're solving for angle. So now we're solving for values of x, y, and z, and z is an angle. So all right, let's get started. So DEF, so angle D is equal to H. So HE is equal to J, and then F is equal to G. And again, what I'm doing is I'm using these as reference points because it's easier to do that than it is to worry about using the picking them up and rotating them around and switching them. Again, if you know that what you're doing, if you know that the side you're looking at is between angles 2 and 3, it doesn't matter how they shape it, it doesn't matter how they move it, it doesn't matter how they alter the image. The side between angles 2 and 3 is always going to be the side between angles 2 and 3. So I'm going to go ahead and get started with the angle one. So angle one is going to be on the small one is 88, on the big one is 11z. So here's the thing about angles. Angles are if you have similar triangles, the angle measurements are going to be the same. They're not going to conform to the scale factor. They're not going to be bigger than the other ones. They're not going to be smaller. They're going to be the exact same measurement, because it doesn't matter if your sides are all 3, if your sides are all 6 with a triangle. If you have a triangle with all the sides of 3, if you have a triangle with all the sides equal to 6, all the sides equal to 9 or 12 or what have you, the interior angle measurement of all 3 of all of those triangles is going to be 180. And if all of them are exactly the same, they're always going to be 60. And so even if they are similar triangles of different sizes, the interior angle measurements, or the inside of the triangles with the angles themselves, are always going to be equal. So what that means is 11z equals 88, because these are proportionally the same angles as I mentioned earlier. So that means that z equals 8, first one down. All right, now I've got to worry about x and y. Well, what I have here, I have a number between angles 1 and 2. I've got 2 numbers. All right. So that means I've got 2 numbers. So what that means is I can set this up so that 15 goes to 9 as, let's see, I've got between 1 and 3. So 1 and 3 as 12 is to x, and as 14 is between 2 and 3 is to y. So yeah, so again, I've got, knowing the angle, so the angle measurements are going to be exactly the same. So what that means is, if I'm going to find any of the other sides, I have to have something of a scale factor. I have to have one side on either I have to have 2 sides of the same, I have to have these two. If I'm going to be solving for a variable, I have to have one side of the triangle where I know both of the numbers. I have to know both of the numbers on the same side of the triangle or on the corresponding sides of the triangle in order to set up my scale factor. In this case, the side between angles 1 and 2, or in this case angle 1 and 2, I had a number for both of those. So going from big to little is the same as going from 15 to 9. So I was able to set up my ratio that way. So going from big to little, 14 to 9, oops, is the same as going from x to 12. And it's the same as going from y to 14. There we go. So what does this mean? What this means is I'm going to set it up as two different cross multiplications. I was just writing it out as one line to illustrate the point. But in terms of solving them, I'm just going to be looking at 15 and 9, and then x, I'm going to be looking at these two when I'm solving for x, and I'm just going to be looking at these two and solving for y. So that gives me 9x equals 15 times 12 equals 180. So x equals 20. So I got that one. And then finally, 9y equals 15 times 14, 210. So that's going to, let me clear that one up again. 210. So 15 is to y is 9 is to 14. So 9 times y, got that. 15 times 14 equals 210. Alrighty. 210 divided by 9. Alrighty. Y equals 23.3. So there we go. That is x, y, and z with knowing two similar triangles. Again, starting out, we know that the angles are equal. The interior angles are always going to be equal. So all I did was I went through given the names. I said this is angle 1, this is angle 1, this is angle 2, this is angle 2, this is angle 3, this is angle 3. And I went through and I labeled the angles, and I noticed that angle 1 on both of them gave me my equality. Well, I know that 11z is the same angle measurement as 88, so 11z equals 88, solve through it that way. With x and y, I had to do something with 15 in the hopes that the side that was between angles 1 and 2 had a number attached to it on the small triangle, and by George it did. We're in great shape now, because now I can set up the ratio. I can raise the ratio or the scale factor so that I have whatever the measurement for the big triangle is to the small one. And so that would allow me to solve for x and solve for y. So let's see that again with another similar triangle. So if these are both going to be similar to one another, find the values of x and y. All right. So I'm looking at this right now, and I know for a fact that L has to be equal to one another. Whatever else the other proportions are, I don't know. I just know that L has to be equal to one another because they're vertical angles. And if you remember from Unit 2, it doesn't matter what else is going on. If you have two intersecting lines, if you have two intersecting lines, the angles that share a common vertex but not a common side are always going to be equal to one another. So I know angle L, regardless of what else happens, is going to be equal to itself. So we'll start out knowing angle L is equal to angle L. All right, that's kind of a validation of my system of naming the different angles. So I feel pretty good about that. Well, angle L is going to be 1. I'm just going to let angle J and N be angle 2. And again, these are just purely arbitrary designations. I'm just making them just to differentiate them out. And then that means that angles K and M are going to be angles 3. And so, again, the reason that I label these angles is so that I have a common reference point between the two similar triangles. Let's see. So I have to find the values of x and y. Let's see. I've got N and M. N and M are between 2. So N and M is 16, and that's between angles 2 and 3. J and K is 40 between angles 2 and 3. All right. So from big to little is going to be equal to the ratio of 40 to 16. All right. Well, we're in good shape there. So the side for x is the side between angles 1 and 3. The side between angle 1 and 3 here is to 14. So side x is the big to the little, which is 14. And then y is the side between angles 1 and 2. Angle 1 and 2 is 45, so big is 45. So big, aha, caught myself there. Big one is 45, small one is y. All right. And so again, I'm going to do what I did up here, but I'm just going to do it down here. I have the same scale factor listed here. I'm just going to apply it to x first, and then I'm going to apply the scale factor to y, and I'm just going to do the cross multiplication twice. So that gives me, so for x, that gives me 16x equals times 14 equals 560. X equals 560 divided by 16, 35. And then for y, I have 40y equals 16 times 45, 720. Y equals divided by 40, 18. And kind of do a quick reality check also. X equals 35, does that track? Well, 35, 40, and 45, those are close to the same sizes, and this one's definitely the smallest one of the three, so that kind of checks out. For y equals 18. Y is the same proportionate size as the 45 is, so y has to be larger than 14 and 16 proportionally speaking. It is, so I feel pretty good about those numbers, not just because I saw the answer key. All right, so moving on. This one looks rough, but it's really not that bad at all. I've got, as most of them are, so I've got AGM and KXD. So angle A is the same as angle K. G is the same as angle X. G, same as angle X. This is going to get pretty busy here. And then M is the same as angle D. 1, 2, 3. 1, 2, 3. All right, well, that one wasn't too bad. And I have to find the values of X, Y, and Z. Oof. All right. Okay. All right. No, I'm not going to do that. Well, let's go one at a time. So angle A and angle K are the same, so I don't have to worry too much about that. Let's see, so here we are. For Y, I've got angle X is angle 2 on this one, and angle G is 2 angle on this one. So 2y plus 5, because if you remember, the angles of similar triangles are going to be the same. So 2y plus 5 equals 65. So 2y equals 60, subtracting 5 from both sides, so y equals 15. All right, that's one down. Let's see. Where is Z? All right, so Z is M. Oh, here we go. All right. Oh, these guys are tricky. These folks are tricky. All right, so if I know that y equals 15, what I'm going to do is I'm going to feed it back into this equation. And so 2y plus 5 is, so 2y plus 5, oh wait, I don't need to do that. I've already done that. So this is equal to 65. So if this angle equals 65, and this angle equals 63, so 65 plus 63, these two angles equal 128. If you remember what I was mentioning earlier about measure of angles, the interior angles of triangles, they all add up to 180. So 65 plus 63 is 128. 128 from 180 is equal to 52. So that means that angle D is equal to 52. Well, who cares, right? Well, I care because angle 3 over here is angle 3 over here, which means 4Z plus 4 equals 52. Now that's devious of them. So that means that 4Z equals 52 minus 4, 48. So divided by 4, 48. So that means that Z equals 12. All right, we are making some progress here. We are doing pretty well. So what I've got here is, all right. So, ooh, here we go. This is gonna be rough. So the two sides that I have are between angles 2 and 3. which is x plus 6, and then between angles 1 and 2, which is x plus 3. All right, so I don't know which side is bigger, I don't know which side is smaller, because all I have to go on are the angle measurements, which are exactly the same. So it really doesn't matter how I set up the ratios, as long as I reference the same triangle. So I'm going to label this one triangle 1, this one triangle 2. And so as long as I have a ratio going from 1 to 2 and then 1 to 2, I should be okay. So what that means is I'm going to look at sides, look at angle 2 and 3. So 2 and 3. So x plus 6 is to 36. So I'm going from 2 to 1. So I'm setting up my ratios from 2 to 1. That's just completely arbitrary. The labels are, as long as you're going from one triangle to another on one ratio, as long as you're referring to the same relative sides on the same triangles, you can set the ratio up this way. So x plus 6 is to 36, because they're the sides that are between angles 2 and 3. X plus 6 is to 36 as, let's see, yep, 1 to 2. So angle 1 and angle 2, the side between angles 1 and 2 is x plus 3. And the side between angles 1 and 2 is 32. Oofa. All right. So what this means is that 36 times 3, so 36x plus 108 equals 32x, 32 times 6, plus 192. What I'm going to do is I'm going to subtract 32 from 36. That's going to give me 4x. And then I'm going to subtract 108 from 192. That's going to give me 84. And so I divide both sides by 4. X equals 21. Wow. All right. I'm not going to lie, that one was a little rough, even by my standards. But again, even though I'm throwing a bunch of this stuff out there, like angle 1, angle 2, the side between angle 1, angle 2, all those designations are completely arbitrary. They are, all I know based on the similarity statement here is that these are the angles that are proportional to one another. And so if those angles are proportional to one another, then that means that the sides that are between those two angles are going to be proportional to one another as well. And if the sides are proportional to one another, then that means that I can set up the ratios and the scale factors in order to solve for the missing values. And it doesn't matter how complicated some of these are, as long as you remember a couple of details, like the interior angle measurement of a triangle is always going to be 180. Well, that enabled me to solve for z. That enabled me to solve for z. Then once I knew that both of the x's that I was trying to solve for had a number attached to them proportionally, then I could set up the ratio and then solve for x that way. So again, you don't really need to have the scale factor. As long as you have 4 numbers, you can kind of solve for pretty much anything, even if they do have some pretty ugly variables with them. So here we go with this one. This next one looks rough, but it's really not that bad. So we have triangle TLY to CHK. So T is to C, as L is to H, and Y is to K. Okay, so I have to find the perimeter of each triangle. Well, TLY is going to be easy. That one's going to be easy. It's going to be 25 plus 35 plus 30. And it's going to equal 90. Now I think there's a shortcut to doing this, and I'm going to try that shortcut out. And if it works, I'll tell you about it. If it doesn't, I'm just going to move on. Let's see. So let's go with. Okay. So just ignore that writing off to the side. I think it's a theory of mine. I want to make sure that I do it that I do everything I'll show you the shortcut after I show you the long way. If the shortcut works. If it doesn't, I'm just going to move on. So I've got 25. So the side between angles 1 and 2, I've got numbers for them. So what that means is I've got 25 is to 10. And these other sides aren't labeled. These other sides don't have labels on them. So I'm just gonna put them on there, X and Y. And the idea being that if I'm going to solve for the perimeter, I need to know, here we go, I need to know what these values are because I need to be able to add them all up, right? So knowing the scale factor and knowing that these two are similar, the scale factor going from large to small is 25 to 10. Well, let's take a look. I got the side between angles 1 and 3, which is side between angles 1 and 3. That's 35 on the big one, and X on the small one. And then I've got the side between angles 2 and 3, which is 30 on the big one. And the side between angles 2 and 3 on the little one is Y. So what I'm going to do is I'm going to solve for sides X and Y. And then once I solve for X and Y, I'm going to add them all up. I'm going to add up the whole thing for the perimeter, and that should work out. So for X, that gives me 350 equals 25X. And so 25X, 350. So X equals 14. And then the same thing for Y. 25 times Y equals 30 times 10. So Y equals 300 divided by 25 equals 12. Alrighty. So I've got X equals 14. Y equals 12. So now I'm going to add everything up. So I've got 14, 12, and 10, which gives me 36. So that's yeah, that's pretty good. So that's how we can solve through it that way. Thankfully, my shortcut panned out, so I'm just going to go ahead and tell you this. The perimeter also scales. So if you know the perimeter of one and you know the scale factor, you can scale directly to the perimeter of the second one. So the way that I know that is, I'll show you over here with bigger type. So with bigger type, so you can see what I'm doing. So originally I only knew 25 and 10. So going from the big one to the little one, I only knew 25 goes to 10, right? That's my scale factor. But perimeters also track. Perimeters also scale, and they also scale proportionately with the scale factor. So 25 goes to 10. The perimeter of this whole thing is going to be 35 plus 25 plus 30 equals 90. I'm just going to use Z for an arbitrary constant, for just an arbitrary number. So if going from large to small, if this is the scale factor going from large to small, which is what I've got, 90 is the perimeter for the large one. Z should be the perimeter for the small one. So let's solve that out over here on this space. So I've got 25Z equals 900. So 25Z cross multiplication equals 900 cross multiplication. 900 divided by 25 equals 36, which is the same as what we calculated over here. So this was from the last worksheet where we had to. It was from the last worksheet when we were introduced to scale factors, and they didn't really go into. They kind of glossed over it, if I'm being honest. Yeah, they definitely glossed over it as a detail, but I remembered it because I'm recording all of these at once, so I literally remember it from like about 20 minutes ago. So yeah, perimeter scale over also. Just kind of keep that in your back pocket. All right, last one, and it really is the last one. Let's see. ABCD is proportional PQRS. Oh, all right. So if A goes to P, B goes to Q, R goes to C, and then S goes to D. 1, 2, 3, 4. 2, 3, 4. All right. Find the perimeter of each polygon. Oh my goodness. I made this way harder than it needs to be. All right, so yeah, I'm just going to erase these. These aren't necessary. I apologize. These aren't necessary for this particular problem. So remember way back when I was talking about triangles and how you indicate sizes with triangles, how one hash equals, how if you have one side that's labeled with one hash, and then one side labeled with that same one hash on the same polygon, then it means that they're the same length. Well, that's actually very elegant proof of that right here. So this, I'm not sure, it doesn't really show up well on the screen, but if you look at the worksheet, it does. This is one hash mark here. This is one hash mark up here. Remember, if you have the same hash mark or the same angle measurement on the same part of on a different part of the same polygon, it means that they're equal. So that means that that is 25. It also means if we go over this polygon over here, that this side is 20 and this side is 14. So find the scale factor of ABCD to PQRS and the perimeter of each polygon. So the scale factor of ABCD to PQRS is going to be, so they're telling us going from ABCD to PQRS, scale factor is going to be from small to large. Well, what sides do we know? We know 20, we know 25. All right, so scale factor is going to be 20 to 25. Now, there are two schools of thought as far as simplifying scale factors are concerned. I am of the opinion that if you have the scale factors as they are, like as it is right now, I'm perfectly fine leaving the scale factor the way it is. And if we were on a test or an assessment and you left the scale factor that way, I'd be perfectly fine with it. There are other math teachers that will say that it's more important that you simplify it down to its smallest value, that you treat these as reducible fractions. And so that means it would be 4 to 5. Honestly, given that the calculator is going to do most of the work anyway, simplifying the fraction down is just another source of error because it's another computation. And what I found, especially teaching, is that the easier that you think the operation is, the more prone you are to make a simple mistake, because you think that you can't possibly make a mistake over stuff that's that easy. So again, if you left it as 20 to 25, I would not mark you against it. I don't think that there's anything wrong with leaving it the way it is because it also is a more direct representation of what you see. So for my part moving forward, I'm going to leave it exactly as I find them. If you feel more comfortable reducing them with fractions, that's perfectly fine. I'm certainly not going to ding you if you chose to record the conversion factor as 4 over 5. What I will ding you for is if you get the conversion factor wrong. If you try to reduce it, you get the conversion factor wrong and your numbers are thrown off. Then I will definitely ding you for it because you had an alternative that would have eliminated that source of error. Anyway, we know, so we have our conversion factor. We have 20, we have small to large, we have 20 to 25. Now we just need to find the perimeter of ABCD. Well, like I mentioned before, if you have 2 hash marks on this side and 2 hash marks on this side, on the sides of the polygon, that means that these are both the same length. And so I've got one up here, I've got one down here. That means that these two are the same length. So what I've got is 20 plus 20, which is 40, plus 14 plus 14 plus 28. So the perimeter of ABCD is going to equal, they don't really give us any numbers, so I'm just going to say 68. They don't give us any units, is equal to 68. So that's the perimeter of ABCD, which is 14 plus 14 plus 20 plus 20. All right. Now the perimeter of PQRS. We know what the scale factor is going from small to large, so that's all I'm going to do. I've got the perimeter for the small one. I have the scale factor. I'm going to get the perimeter of the large one. So 20 is to 25 as 68 is to x. So x, erase this. So 20x equals 68 plus, not plus, times 25 equals 1700. And then divide that by 20. That gives me 85. And that will be your correct answer. So again, as long as you remember that if you have similar polygons, if you have similar shapes, whether they're quadrilaterals, pentagons, heptagons, or triangles, if you know that they're similar, then if you know they're similar and you know their scale factor, then you pretty much know everything you need to know about all of them moving forward. So yeah, on to the it's a short week this week, so on to the assessment review. If this isn't itself the assessment review.